Welcome to a new test and teardown video. This time it's a power supply from Hewlett-Packard. A model 6433B DC power supply. 0 to 36 volts and 10 amps. So that is 360 watts of output. Nice! This thing weighs 16 kilos, so it's quite heavy. And it was released in 1966. And if we have a little look through the top, we can't see that much, can we? But we can see tiny little heat sinks here at the back. And I will dig a little bit into that very, very soon. Why are they so small? Because that will be the 4 rectifier diodes, and that will be the 2 SCRs. Yes, this is a switch mode power supply, not a linear power supply. But it's working on mains frequency, a mains frequency switch mode supply. Ha! I am impressed. So let's look a little bit closer on the internal parts. But probably before we go and explain everything in here, I think you should go and click on the video link I have written in the description. This is a video link to Colin's video, also known as video 99, about exactly the same power supply. This is only a 3-minute clip, but it's really, really good, and it explains the funny thing about the current spikes. Obviously, there will be in this power supply because of those two are more or less directly connected to your output. So you're going to get a nasty current spike when you're using the current limits, because this is what you're gonna get on the output, right? So please come back after the video. So hopefully you are now back after watching Colin's super video, and I can show you the schematic of this fantastic power supply. There are those 4 major things I want you to note. Of course, the output capacitors. We got the inductor. So this is the smoothing inductor, and obviously this is very, very little for the frequency. So it's only for the harmonics and high frequency oscillations and stuff like that. You want to smooth just a little bit, because in a real world, this inductor should have been the same physical size as the transformer to be able to contain the energy for the amount of time. So as you can see, it is much smaller, so that means that is not their intention. Then you got transformer 2. This is the auxiliary power. This is what drives everything here, because the main feature of this power supply, that is the 2 SCRs. They turn on and off by mains frequency and pulse width modulation. So at each halfway wave of the mains input, you can turn on and off that wave into the transformer primary side on. In this case, as you can see here, it's wired for 230. It's quite nice, nicely explained here on the transformer. So we know this unit is correctly set up for Europe power level. And then we have, of course, the rectifiers, a little bit of filter components, current measurements, and all that kind of stuff. But it's fairly simple power supply, and I kind of like the idea. But of course, when you're running this at mains frequency, you need very, very big capacitors, and also your regulation loop speeds, and of course the peak currents will be very, very high, and that is just a side effect of all this. But that is already written just exactly as Colin explains. It is written in the manual, so everybody should know this, that this one is not for laboratory experiments of small sensitive electronic setups. This is for high power stuff that can handle a lot of peak current, and you probably want to drive a lot of power, a high voltage, high current, and you don't want burning hot power supplies. And this is exactly what this power supply is used for. And so as long as you use this for its correct design and intentions, then there isn't any problems really. Let's see if it works. So let's try and power this up for the very first time. I did already connect my load so I can see the output voltage. Everything here is just in the middle. So we'll see what happens, right? So let's give it some mains, and hopefully nothing happened, and that is exactly 476 watts. But I did heard, I don't know if, did it come on the video? I don't know, but I could hear that it was trying to charge those capacitors to 20 volts is what we have. And yeah, we got 21 is what we have on my load. So far, it looks like it's working. I have a little bit of unstable here. Let's just try and give it 0.2. That is, of course, not a lot, but this is just our very, very first. Super careful. 1 amp. And can you hear this? And this is of course normal. It's because it's clipping mains into sharp edges. So of course they make this transformer sound like this. Let's go closer and see if you can hear this. Probably coming from all this. Nice. So output. This is going to be quite interesting for you guys to see, by the way. My output is 21 watts, okay? And at this low load, 30 watts of input. So of course there's a super high efficiency. What we could do is crank up the voltage to 30. Like that, right? And then output is of course now 30 watts. And input is 42 watts. That is very interesting. And that is very, very good for 1966. Let's crank up and every time I crank up the load, you can hear it go boing. So this is 3 amps of output. We don't want it to go into current limit. This sound is just scary. 91 watts of output and 112 of input. I'm gonna go and let it run for a little while and find my thermal camera. So let's have a little look how this looks on our thermal camera. So there's a resistor down there. That's it. And yeah, that one there, I believe this is the current sense resistor. So of course that one is a little bit warm. But that is all our loss is more or less hidden in that power resistor, and it's 80-90 Celsius, and it's located quite close to those two capacitors, so I'm not super happy about that. But that's all, more or less. Yeah, we got... That's not warm in any way. Look at the primary side SCRs. They're probably not even awake yet. That will be the 4 low voltage output rectifier bridge. But super nice and ice cold power supply from 1966. So let's look a little bit on the output ripple. This is only 20 millivolts per division, so it's a super weak signal, right? And this is 2 amps, 3 amps, 2 amps. So every time there is a load step, the output voltage goes a little bit like that. And of course, it will take some time to regulate and handle those 2 big capacitors, though this is 100 watts and 60 watt and 100 watt, right? Let's zoom out a little bit and let's see if we can get a better view on what is going on. Look at that. So here's the step response. Now I'm zooming out on time, and then I'll do a little step. 3 amps, 2 amps, 3 amps, 2 amps. And then you can see what's going on. But this is 100 millivolts per division, and the output voltage is 30 volts, right? And this is probably not a big deal for a lot of things. You can't compare this with a linear power supply, but they also do these things, but it's just much faster and much less, obviously. But if we let's try and look at this in relationship to the full output voltage. Here is how it looks like. This is our 30 volts. Here is 0 down that line, right? And I set it a little bit over. My trigger point is right here, and I got now 100 milliseconds per division, so you can see this is the overshoot at every load dump. And this is only 2 amps, so I'm gonna start 2 amps, so I'm gonna give it 3 amps like that, and then we're gonna kill the load, and then you see this little change. I can of course do it like this if I want instead, and then it will no, there isn't a lot of load drop, but there is some load peak here when I have a load dump like that. Oi, look at that. But anyway, it really works. That is fantastic. So let's try and crank it up a maximum load test here. I think I did change my fuse in my Vario, so I should be able to load this. But if we have a disruption here, that will be the case. I have now set the output voltage to 36 volts. And let's try and crank up the current, see what happens. So that's 3, 4, 5, 6, 7. So 7 amps of output is 253 watts of output, and power consumption is 308. 8 amps. No, oops. Oh. That was a power overload on my load. Oh, I need to go and get another cable. We need to load some more. So here was my problem. I was of course trying to do this with only one load, and that is just stupid. So let's crank up the first 5 amps on one load, And let's turn on the other one. And let's crank up the other 5 amps. So now that is 10 amps of output, okay? 360 watts of output. Yeah. And my input is only 449. That is nasty. I better turn this off. The sound is just terrible. But yeah, it is definitely delivering 10 amps. Nice. Let's look a little bit on the block diagram of this switch mode power supply. It's not super detailed, but that's the whole idea about a block diagram. But what we can see from this is the SCR regulator. It's a sort of an on-off switch, is connected before the mains transformer in the middle. To the right of the mains transformer, they have this they call main rectifier and filter, and then we go to the output to the right. I think this block diagram isn't really that good, so I think we should skip directly to a regular schematic. The schematic looks like this. I have added some text here to make it a little bit more clear where we are and what is going on. So again, we see the 2 SCRs now between the AC input and the main transformer. Those 2 SCRs, they work of course only in one direction. So once you trigger them, they stay on until the voltage or current goes to 0, and then they release being on, and then they will be open until they are triggered again. If you see the trigger transformer, it actually activates both of them at the same time, and there's only one transistor, the little Q7, that activates both of those 2 SCRs at the same time. However, one of them will of course only be triggered because there's only current going in one of them in this particular cycle. If it's the positive or the negative AC cycle, then you trigger the positive or the negative SCR. So that's quite smart the way that they have done it that way. On the primary side, left of the SCRs, you don't really see any big filterings or anything like that. There's only one little 1 microfarad capacitor, and that is all. No big inductors or anything extra. So I don't know if this will pass the harsh requirements of today's EMC standards or CE norms, all these kind of things. Especially for emission or pulsings or harmonics into your mains. So, but anyway, it kind of didn't affect any of my equipment here. No lamps or LEDs were flickering and nothing bad happened. So I'm quite happy about it that way. On the output side of main transformer 1, you of course see this bridge rectifier, and then you have the first mega big capacitor. So this is the 40,000 microfarad capacitor, and we have 2 of these in this unit. Then we have L1 for filtering, and as I mentioned earlier in the video, this inductor is of a very low value, not far from needed to smooth out all this energy in this time that we're dealing with here, because this is mains frequency. And then you have a shunt resistor at the top for the constant current and current limiting systems. And then there is another one of the 40,000 microfarad that is directly connected to the output. And of course they try to filter and isolate all the little high frequency ripples and stuff like that, and this is why they have the inductor in one side and then the current sensor in the other side, and then the last capacitor is directly on the output. But of course when it comes to short circuit peak pulse currents, you could consider those two capacitors being in parallel, and you will get a current, a short circuit current that is only limited by the internal resistance of those two capacitors. So the current will be significant, definitely. There's not a lot to say about the voltage sensing, voltage bias, reference, and all that kind of stuff. This is a basic circuits, really. I don't want to go into super detail about how that is working. You should just inspect this schematic if you want any further details. So I've been looking a little bit at the meters here, and this little piece of plastic up here, I think this reveals those meters are also used together with top lights or top lights. So I definitely think that we can definitely shine these and make them look real nice. So I found some LED bands, and I'll try and see if I can solve this with a little wire and solder these here on the top, and take the wires down here. And I think these two capacitors will be the plus minus 30 volts for the auxiliary supplies, right? So that is what I'm gonna use to drive the meters. So look at that. That went absolutely a lot better than expected. Really, really nice with all that light, and it's so easy to read the meters now. I want you to see all that I did. I put those little LED strips here, and I taped all the way around the meter, twisted all the wires, and I mean, so easy. It took me one little test to figure out the series resistor for the voltage. That one here is connected to that capacitor, and I did of course mount the two 12-volt strips here in series, because I wanted to use the highest possible voltage, because I got 32 or something like that on those caps, or the left one, right? So that is all I wanted to show you in this video. So thank you very much for watching.
Remember to like and subscribe.